Hello, and welcome to our presentation for the Mackay 2024 Unsure Workshop titled Conformal Prediction and Monte-Carlo Inference for Addressing Uncertainty in Cervical Cancer Screening. The general idea of this project is to take a model trained as part of a cervical cancer screening pipeline for use in low and middle income countries and understand when and why it is uncertain about its predictions. In order to do this, we will be using conformal prediction for uncertainty quantification and an uncertainty quantification derived from Monte-Carlo inference. Briefly, conformal uncertainty quantification seeks to create prediction sets with the classes that would be selected as outputs of the model to reach a predetermined coverage, 90 or 95%. In this project, we use two algorithms, the least ambiguous set valued classifier and the adaptive prediction sets, but in this presentation, we're going to focus just on the LAC. For the Monte-Carlo method of uncertainty quantification, we train the model with dropout, and then at inference, leave dropout on and run 50 inferences. We take the expected value of each inference and then find the coefficient of variation of those 50 expected values. This gives us our two methods of uncertainty quantification for this project. The dataset used for training, validation, and testing was an international study with about 17,000 images taken during a colposcopy of a cervix, and the particular out-of-distribution dataset that we'll be running inference on and analysis with this project has 1,348 images that were chosen by the team as the out-of-distribution dataset after model selection. The model in question is a DenseNet 121 with ImageNet pre-trained weights, and the classes are normal, gray zone, and precancer plus. The three main tasks that we'll be exploring in this work are the connection between conformal uncertainty quantification and model performance, the connection between conformal uncertainty quantification and Monte-Carlo uncertainty, and finally a comparison of uncertainty for the gray zone class in the 3 and 2 class models, as this class is considered to be the most uncertain. Now moving on to the results for the first task, where we look at the average prediction set length of the conformal predictions. This is our metric for conformal uncertainty quantification and model performance. Recall that we want a low prediction set length. 1, for example, would mean that the model was very certain, whereas a prediction set length of 3 meant that the model was uncertain. So we can look at various subsets of the classification results, such as correct versus incorrect, correct versus single class misclassifications, so from normal to gray zone or vice versa, or correct versus 2 class, so normal to precancer and precancer to normal. And we can also look at the individual ground truths, saying when the ground truth was 0, which is normal, how did the model perform? What was the average prediction set length? And we can see that in general, when the model is correct, it has an average lower prediction set length than when it is incorrect, with the notable exception of ground truth 1, which is the gray zone, which, as we said, is generally a very uncertain class. And this is an important result for use clinically because it means that we can use the uncertainty as another piece of data for the decision-making process. Moving on to the results for task 2, the connection between conformal uncertainty quantification and Monte-Carlo uncertainty. We see here that we have a Spearman rho value of 0.58, indicating a strong correlation that is statistically significant between the average conformal prediction set lengths and the coefficient of variation of the 50 Monte-Carlo expected values, meaning that these two methods of uncertainty quantification, while not quite the same, are in some sense capturing a similar underlying uncertainty. Moving on to our final task, a comparison of the uncertainty of the gray zone class in the 3 and 2 class models. We will look at the table on the left, the 3 class model, where we see that the gray zone on average has a higher prediction set length than both the normal and precancer plus, indicating it is more uncertain. However, we note that it is not statistically significant at the 0.05 level, the difference between the average prediction set length of the gray zone and precancer plus. Moving on to the 2 class model on the right, the gray zone images were all originally classified as normal, so we can look at the average prediction set length between the normal images and these images that were reclassified as gray zone, and we see, of course, that they are statistically significantly more uncertain. We can summarize our results by saying that, in general, the model is more certain when it is right, and vice versa, and that this is a clinically relevant finding. There's a strong correlation between the average conformal prediction set length and our defined Monte-Carlo uncertainty metric. And finally, that the gray zone class is very uncertain in the 3-class model, along with precancer plus. And in particular, that the images given the gray zone label in the 3-class model are statistically more uncertain than in the 2-class model. And this is a good argument for the inclusion of this 3rd class. Thank you very much for your attention. I look forward to seeing you in Marrakesh.